thank the organizer, as usual, for arranging this nice workshop in the beautiful city of Granada and for allowing me to be here. I think this work is very, very mathematical, so I tried to sketch the story of what we've done. And the main point is the existence of Hadamard states in every global hyperbolic spacetime for massive vector fields, so for the Proca fields. Okay, problems that actually are not problems, but are necessary conditions to describe a vector field. So Proca operator is not normally hyperbolic, so it is not a Klein-Gordon operator or a wave operator. So it's a little bit more tricky to study the Cauchy problem. Second thing, the four vector fields do not admit states due to lack of positivity. And this is something that we know easily from even in Minkowski spacetime. If one tries to quantize a four vector field that obeys Klein-Gordon equation, you necessarily end up with negative norm states. And then the existence of Hadamard states had been proved, but not in general spacetimes, but just Cauchy compact global hyperbolic spacetimes. Moreover, the definition of Hadamard state was very specific to the case of the Proca field, and actually we proved that the definition is equivalent to the standard one that I will give in a few slides. Okay, the outline is try to a little bit do a recap of what algebraic quantum field theory is. Then I will talk about classical Proca field and its CCR quantization in the spirit of AQFT. Then I will talk about the construction of Hadamard states on ultrastatic global hyperbolic spacetimes, very briefly, just a few words about it. And in the end, I will discuss the strategy that we used to prove the existence, not just on ultrastatic spacetimes, but on general global hyperbolic spacetimes. And the two tools that we used that are the paracausal deformation, that is a completely geometric topic, and the so-called molar operators. And everything is based on a paper that you can find. It's been accepted for publication on Analyse Poincaré with Valter Moretti from University of Trento and Simone Murro from University of Genova. Okay, so AQFT, very brief recap. In AQFT, you have a smooth global hyperbolic spacetime, and you assign to regions open subsets of the manifolds algebras that satisfy very natural properties. So when you restrict the region, of course, you have a way to restrict the algebra of the observables. If your region contains a Cauchy hypersurface of the global hyperbolic manifold, then you have an isomorphism of the algebra associated to this region to the algebra associated to the whole manifold, and it's some way reasonable. And then causality. Causality is just Einstein causality, and says that if we have causally independent regions, the observables, actually all the operator algebras associated to these regions must commute. Okay, to this algebra, we associate states that are ways just to assign to every abstract operator in the algebra a number. These states must be normalized and positive. Positivity is very important because the existence of states in this sense implies by the Gelfand-Naimark-Segal construction, this reconstruction theorem, the possibility of representing this algebra on Hilbert spaces, so with positive products. That's what we want. To the states, of course, we can associate the endpoint functions that give all the information about the states, the action of the states on the observables. Okay. What is Hadamard state in our sense? Maybe it's a little bit different from the form that we've seen until now of the Hadamard state. But this condition that is formulated in using microlocal analysis and the notion of wavefront set is essentially equivalent to the existence of the Hadamard parametrics with the Hadamard singularity. We are just saying in this thing that locally the singularities of the 2-point functions look like the ones of Minkowski vacuum, nothing more. Wavefront set is just the set of points where the distribution is singular, with also the direction in the cotangent space where where the distribution is singular. So it's not rapidly decaying. Moreover, we consider Gaussian states because we are dealing with free theory in some way, but on a globally hyperbolic background. Okay, now we get to the Proca operator. Proca operator is the second order differential operator, where D is the standard differential and delta is the codifferential associated to the metric. Gamma are the sections, are the one forms. Okay, it is not a Klein-Gordon operator, but it is equivalent to a constrained Klein-Gordon operator. So using that operator, identity plus d delta over m squared, that of course exists just if the mass is different from zero. If the mass is zero, we go to a completely different problem. So we go to gauge theory. We can define those operators that are the retarded and advanced green operators of the Proca field, and that one that is the causal propagator of the Proca field, just by composing this map with the operators of the Klein-Gordon operator. So in some way, this operator that we are using enforces the condition that the field A must be co-closed. Okay, so how do we define this algebra? The algebra is just generated by abstract operators associated to all compactly supported sections of the bundle we are studying, that is the cotangent bundle, so all compactly supported one forms. And we associate operators to sections in a way that is linear, Hermitian, in the sense that if we are dealing with a real field, okay, the star is just the dagger. In physics literature, it's more common to find a dagger. So the field is Hermitian because it's a real field, but everything works also with the complex field. And we impose the canonical commutation relations in that sense using the causal propagator of the Proca operator. Moreover, we ask that the field is on shell, so satisfies in some way the equations of motion in a distributional sense. So what does this CCR algebra have to do with the axioms we said? It's just easy to see that whenever we take sections that are localized in a specific region, we have that we obtain the algebra associated to that region. Okay, so very briefly what we've done. We took an ultrastatic globally hyperbolic spacetimes. We explicitly constructed the state on space-like Cauchy surface. The problem in non-compact Cauchy surfaces is that we don't have in general Fourier modes. So the solution came by using techniques of pseudo-differential calculus and microlocal analysis. Okay, then a four-vector field admits no states. To prove the Hadamard condition, we used a four-vector field where one of the scalar components has the wrong sign. I think that this is quite easy to understand. But then the positivity is restored when we impose the constraint. That is clearly the same thing that happens in Minkowski space-time, easily and smoothly generalized. Okay, the point is that now we have just a state on ultrastatic spacetimes. We want to move to general Hadamard states on general spacetimes. So if we have this kind of relation that should be familiar to you if you know, for example, Gero's paper on domains of dependencies about causal stability, it's a little bit different because this is not strict. But we have that the light cones of the metric G are included in the ones of the metric G prime at each point, or the opposite. Whenever we have this, we can find a function that is 0 in the past of one Cauchy surfaces and 1 in the future of another Cauchy surface in the future of the previous one, and glue the space-time building this kind of interpolating space-time. To this interpolating space-time, we can associate an interpolating Proca operator with the same mass. And then this is the tool that we use to put Hadamard states in a one space-time, a space-time with metric G to the space-time with metric G prime. These objects are called molar operators, and in some way are an isomorphism of the spaces of solution with spatially compact Cauchy data of the operator P and of the operator P prime. So all the stuff that is inside this operator are just green operators of the Proca operators, or on the space-time G and G prime, or on the space-time G chi, the interpolating one. Then there is the kappa that is an isometry that some way has to deal with the fact that we are changing the bundle metric. And then we have that function rho that takes care of the fact that we are also changing the volume form when we do this procedure. And in this way, we can map isomorphically solutions to solutions. In a non-trivial way, this thing can be pushed to the algebras. So the algebras are isomorphic, and the pullback states through this isomorphism are still Hadamard. So we don't want to stop there because we have chosen a very small class of spacetimes. We want the cones at each point to have an inclusion. We defined the paracausal relation that just says two metrics are paracausally related if we can find a sequence of globally hyperbolic metrics such that at each step we have one inclusion of the cones. So we have the GK as the cones inside the GK plus 1 or the opposite. In this way, we can cover a very bigger portion of the space of globally hyperbolic metrics, but actually we don't really know how these classes are made yet. At each step, of course, time orientation must be preserved, so the inclusion must be of future light cones. Okay, this picture shows the thing. We have a Minkowski spacetime there. We look just at one point. Those cones, of course, have no inclusion at all, but we can find this sequence of cones by enlarging the yellow one with the orange one. Then there is the blue one that is inside the yellow one that is inside the red one. So at each step of this chain, we can construct a Moller operator, we can construct the isomorphism, and we can push along this isomorphism, actually pull back along this isomorphism the Hadamard states, preserving the Hadamard condition. Okay, so this topic has become of its own interest in Lorentzian geometry. But one thing that we were able to prove, that is the important one, is that every globally hyperbolic metric is paracausally related to an ultrastatic one. So at each step, we construct a Moller operator. The Hadamard condition is preserved. So we can construct an Hadamard state on an ultrastatic spacetime following the procedure I sketched before. Then construct the Moller operator, associate to this Hadamard state an Hadamard state in the general spacetime. And in this way, we have implemented a deformation argument and actually know that Hadamard states exist in general. Thanks.
Thank you very much. We have time for questions.
At some point, we studied, let's say, generalization of the Proca field in which the field had self-interactions, and we found the ambiguities there. Mm-hmm. So I was wondering if you could extend your treatment to a self-interacting Proca field and shed some light in this type of ambiguities, which for us are...
By self-interacting, you mean what kind of interaction?
Let's say a cubic
okay.
term. It was crucial, though, that the interaction potential had the minima away from zero to have ambiguity.
Okay,
so
our construction just deals with linear field theories, so with free field theories, and probably this thing can be pushed forward to perturbative algebraic quantum field theory, and in that case, maybe one can see what happens with interactions. But we've done this procedure even with the normal hyperbolic operators, with the Dirac operator. So the point is, this operator proves the existence of Hadamard states. But Hadamard states that we construct, of course, are very depend on a lot of choices, on the Cauchy surfaces, on the gluing, on the paracausal chain. So first, one should be able to remove this. For example, this function chi doing an adiabatic limit to see a state that is more free of this dependence on chi. Then when you have the Hadamard state on general space-time, yes, you can just study perturbation theory and see what happens.
Any further questions for Daniele?
So would it be possible if you compute the correlation function, 2-point function with this Hadamard states, then take the limit of mass going to 0, or is it just assume that the mass are always to be bigger than 0?
It would be nice to be able to take this limit, because I have tried to extend this procedure of modular operators to a gauge theory, and I cannot do it. So I cannot find a way to preserve the algebraic structure. Maybe I can do something with states, but with defining them without passing through the algebra. So if it was possible to do a zero mass limit here, we would be able to include in this framework the gauge theory. But if this was possible, probably in the very beginning, the modular operator of the Klein-Gordon field should be suitable to work with also the Proca field and the gauge field. That's what I believe. And we have not been able to make this thing work, at least for algebras. For solutions, classical solutions, for classical fields, everything's okay. But for algebras, there is a problem. So one could ask, let's not forget about algebras, and let's see what happens to bisolutions. And in that case, yeah, one can try to study Hadamard states in this way. The zero mass limit would be very helpful.
Okay, thank you.